Hello, everyone. Welcome back. We are going to go over some of the interesting things for this linear regression model today. So this lecture here is the number 6, and we are going to make some very interesting change to our model so that we can try to make our model a little bit interested to interpret. All right, so let's continue from our previous lecture. So previously, we create 4 different fits of the model. We basically try to put a single variable into fit 1. So just to get used to the basically reading the summary outputs of the model, trying to see, well, what's the summary outputs actually explains to us, and how the coefficient is being interpreted. And we also try to put multiple variables into our model to see, well, the fits of the model. We compare different models, and we found that if we pass in every single variable from the data sets, not every one of them are statistically significant. So we have to actually take them out to see if it's improved the fits of the model. But today, what we're going to do is basically trying to do some transformations of the data. So as we discussed in the class, again, we can actually try to use a interaction terms to kind of model our fits. So in this case, we can actually try to fit another model right here. So we are basically trying to store a fit 5 right here using a linear models by passing in the medium incomes right here. Not income, but the median price, the housing price of Boston area. And we are going to put in 2 variables here. So the first one will be, again, the lower status of the populations, the LSTAT. And we are also going to include age right here. As you can see, well, I'm actually adding this 2 variable, not by the plus signs. In this case, we are using a star between the 2. So what this star means is to actually include both variables into our model, and at the same time doing an interaction terms for the 2. So basically, in this case, we are expecting to have beta 0, which is our intercept. We have beta 1 that go with LSTAT. We have beta 2 go with age. And we are going to have a beta 3 estimates that go with the interaction terms of the 2, which is LSTAT times age. And again, we're using exactly the same data set, right? So Boston. So let's see what happened. So we run this, we fit the model, and let's print summary. So in this case, as you can see, we have the whole summary output here. So again, the most important things to actually note is the outputs right here for the coefficients. So we have the beta 0, which is the intercept, 36.0885. We have the lower status populations, negative 1.39. We have the age, negative 0.00007. And we have now the interaction terms. So it's LSTAT times the age. As you can see, well, in this case, the age is not statistically significant, very highly not significant, because, well, it has a very high p-value. But the interaction term actually is statistically significant, at least at 2.5%. Well, in this case, what happened is we actually put an interaction term into our models so that we can try to see if the lower status population has anything to do with age that together will affect the median housing price in Boston. As long as the interaction term is statistically significant, most of the time statisticians will tell you you have to also include the age variable into your model, even though it's not statistically significant. It's a general rule to apply. Well, we can also take a look at the performance of this model by looking at the adjusted out square. So in this case, the adjusted out square tells us the model actually explains 55.31% of the variations of the housing prices. And also, the F statistic tells us that this model in general are statistically significant. So none of these betas are going to be 0. Right? So at least one of them are basically has a value that's different than 0. So that means, well, this model is statistically significant. All right, so well, by putting in the interaction term, of course, it seems like a very easy way to implement here. To be honest, if you are using a different statistical package, you might actually want to do it in a different ways because, for instance, if you're using Stata, in some cases, people actually tend to manipulate the data in the data sets in order to run the interaction term. So what they did is basically trying to use this whole columns of data, LSTAT, multiply by another columns of data, which is age, to create a new columns, a new variable, maybe we call this an interaction between these two variables. And then we pass it into our model fits. So same as Python. If you're using Python, most likely you are going to create a new variable, the interaction term variable, so that you can actually use it to pass into your linear regression models. But in R, because people actually written these programs to give us the convenience to just pass in the interaction term and still include the two individual columns into our model, so you don't have to create a new columns for any to basically have any manipulations of the data. So it's a pretty convenient function, I would say. Well, if you think the interaction terms it's easy, well, at this point, well, as you can see, we can actually use another way to make a transformations of our model. So for instance, let's say we believe that the model that we have seen before, let's take a look at the plots earlier. As you can see, the median housing price and the lower status populations ratios has this downward sloping correlations. But it doesn't seem like a straight line it's fitting it very well. So instead, you might actually believe that there is a possibility the line might look more like a curve than a straight line. Well, if we believe that there is a non-linear relationship between the two here, well, there is one very easy way to actually adjust the model here. Well, instead of having a linear equations, so for instance, we can actually imagine the specifications of the model will be maybe the median housing price. It's estimated by a model where there is a beta 0 plus a beta 1, which is taking on this variable LSTAT. And if you do not believe that this has a linear relationship between the two, you can actually create a new variable and do estimates for this beta 2. And this new variable basically takes the form of the square of the original independent variable here. So by taking the square of this variables, LSTAT, what happened is it will make it a polynomial terms. So it's just like a square function. So as you can imagine, this square term actually adds the flexibility to our model to kind of just give you the idea how we can fit this data with a curve instead of a line. Well, let's try to do this. And again, a little things to explain here. So just like the same old thing, we are going to pass in the linear model with the independent variables, not the independent, but the dependent variable, the response, which is the median housing price, and follow with this original independent variable, LSTAT, the lower status population ratios, and plus, in this case, we are not trying to create a new variable in our data set, but we are passing in these functions here. So this I function, it's a very, very useful function. So the I function basically tell R to do a mathematical operations within our linear models. So in this case, we are trying to square the values of LSTAT and put it into our model. And again, we are using exactly the same data sets, Boston. Let's see how it turns out. So here is the summary. As you can see, there's a coefficients output right here that tells us, oh, okay, the intercept here now is 42.862, and lower status population ratio is negative still, 2.332. But we have a square term right here, which is a positive number, 0.0435. And more importantly, all three of them are statistically significant, very highly. And also, you can see the fit of the model, it's much better than when we actually have just the LSTAT model, like in Fit1's model. The overall statistically significant level is still very high, right? So the F statistic tells us that the p-value is extremely low. So this model is very highly statistically significant. So generally speaking, we know adding the square term right here only improve the overall performance of the models without sacrificing a lot. So in this case, well, we should believe that maybe the model is not a straight line, but instead we should actually have like a curved lines. So in order to basically see this in real life, well, we can actually try to use the plot functions, but shouldn't be surprised that we might actually have a plot that looks something we don't expect to see. So let's see. Let's plot this fit number 6 and with a blue lines. So only use the first 2 of the 3. So in this case, well, obviously, well, fit 6 is not going to plot because we have one more variable in there. So this AB line functions can only be plotting with the single variable case. But the general idea is, as you can see, there's a blue line right here that actually plotting out the functions. But again, because, well, the blue line can only show one variable at a time, so it doesn't show you the square terms right here. So it's basically just telling you that, well, if we have a models holding the square term constants, we will have a model lines that fitting the data in this case right here. So one very common questions that people ask in programming is they want to show those regression lines with multiple variable or maybe a polynomial terms, but unfortunately it's not very easy for the programs to actually plot a polynomial lines when you're defining a linear models in R. We will try to see what other graph options later, but for now we just say, okay, well, we at least find this blue line to be a better fit to the data because, well, this blue lines describes the whole model right here that compared to a single variable case, the overall adjusted out square or out square is much higher than the single variable case. All right, so the square term, it's interesting. You can also find out, well, what is this I function does, right, by asking the questions, right? So the interpretations and conversions of objects. Well, if we believe that there is a much more complex nonlinear relationship between LSTAT to the medium sales price in Boston, you can actually pass in a much more flexible models by defining the degree of polynomials. So for instance, we can actually see how fit 7 is being implemented. So fit 7 will run a linear regression model, and it will pass in the medium income housing price that go against, right, that coming from the predictor here, the poly functions with the variables, and within this variables, we are going to take the degree of 5 polynomial. And again, same data we are using. So let's see what it does. So in this case, we are defining a model that runs with 5 degrees of freedoms, not freedom, but 5 degrees of polynomials with the LSTAT variable. So that means we are taking this variable with the power of 5. So we have the LSTAT with power 1, power 2, power 3, power 4, and power 5 in the same model. So let's see how the fits goes. So as you can see, we're creating a polynomial functions. So we have the intercepts right here, 22.53. We have the beta 1, which describes the first power of the variable LSTAT. We have the square term. We have the cubic terms. We have the quadruple terms. And we have the power of 5 for that variable. And as you can see, all of them are statistically significant. Now, it seems like it makes sense to put more and more polynomials terms into our functions to make our model much more flexible to fit the data sets. However, you have to always keep that in mind. Adding more and more terms into our model might not be necessarily the best way to approach this kind of problem. Or maybe in this case, I would like to ask you guys to focus on this adjusted out square. So in this model, when we have 5 powers, we actually have an adjusted out square 67.85% of the variation being explained, compared to if we only have a square terms. To be honest, adding those cubics, quadruplets, and fifth powers of the terms, it's not necessarily improving the model a lot, but we have to add a lot more into our models. So in this case, now it's time for you to realize if adding more and more variables into our models, like in this case, we are adding 3 additional powers to our model, but not necessarily improving the fits of the models, then you have to actually start realizing maybe it's not the best way to add those terms into our models. Even though they are statistically significant, it doesn't really mean that it doesn't come with a cost. And one thing that we haven't really looked at yet in our models is the degree of freedom. As you can see, when we adding more variable into our model, the degree of freedom drops to 500 in this model. As comparing to previous, we actually have a degree of freedoms 503. So we are actually having a higher degree of freedoms when we're not having too many variables passed into our model. So again, well, we will talk more about those technical issues for adding more variable into our model, but for now, those are the numbers you should always pay attention to. All right, so at this point, we would also like to go over some of the very common questions to run our linear model. And in this case, we are going to use a different data set called car seats. So this car seat data set, it's basically coming from the ISLR library. So we can actually take a look. So this car seat data set, it's the sales of child car seats, and it has the variables of sales, price charged by competitor at each locations, income levels, advertising, population, price, and so on. So to actually get all the variable names, again, you can use the name functions. So you're actually getting all the names of the variables here. And you can also print the summary of the data by using the summary functions. As you can see, well, you can actually have all the minimum, maximum, the mediums of the variable here. Well, by looking at the number here, as you can see, most of them are quantitative data. So for example, sales is quantitative, competitor price is quantitative, income is quantitative, but there are something in this data sets, they are not quantitative data. For example, shelf locations, urban, yes or no, United States, yes or no. So those are what we call the qualitative data. So when we are trying to run a linear regressions with the qualitative data, well, we have to be very, very careful. So for example, let's run a regression models fit 8 for taking in the sales of the car seats by passing in all of the variables, and we are going to add the interaction terms of income and advertising and the interaction terms of the age and price. So let's see what's going on here. So let's print the summary. So in this case, as you can see, well, we have a modeled summary here. And you can actually see all this individual variable being passed in. And also the interaction terms right here being defined. So now the thing is, interpreting the variable become very, very tricky now. The reason is because those qualitative variable like US yes, urban yes, has a very different interpretations comparing to the quantitative variable. So for instance, this variable here, let's say, well, urban yes, it basically take a binary or binary value 0 or 1 if this store is actually located in the urban locations. It will take a value of 1. If the store actually has a store locations that it's in the rural locations, then it will take a value of 0. So in this case, the beta that go with this variable is 0.14015. So what it means is, if the store is actually located in the urban area, if yes, it will increase the sales by 0.1401597. But if the store is not in the urban area, right, it takes a value of 0, 0 times this 0.14157, it will become 0. So that means, well, it has no effects to your predictions. Well, same for the US, right? As you can see, the binary choice right here, 0 or 1. If the store is in US, then it will take a value of 1. So it has a negative impact to sales. If the store is not in the US, then, well, it will take a 0 value times a negative number, so it will have no effects to the predicted sales. Well, one very interesting thing to note here is the shelves locations. So as you can see, we actually have 3 values of shelf locations. So if we go back up a little bit to our summary, so this is basically the shelf locations value. It has 3 values: bad, good, and medium. So in any qualitative variable case, as long as you have 3 classes in the same variable, let's say in this case, bad, good, and medium, for 2 out of the 3 classes, you have to create a dummy variable, which is a binary values for this variable in order to run the regressions. Well, fortunately, you do not need to create those dummy variable or create a value for good and medium or maybe bad in order to run this model, because, well, R is going to automatically create this dummy for you guys. Now the thing is, well, you have to actually realize what is the interpretation of this beta estimates. So for instance, if the shelf location is good, it will add the value of 4.8486762 to the cells. And of course, when the shelf location is good, then obviously means, well, the shelf location, it's not bad, it's not medium. So this variable here will drop, and the bad variable will drop. And now the question is, what if the shelf location is actually bad? If the shelf location is bad, then obviously it's the shelf location, it's not good, and neither it's not medium. So in this case, both value will be dropped from the predictions. So you will get 0 and 0 times 4.8486 and 0 times 1.9532. So both of this value will not be added to your predicted values of the cells. So that's basically the interpretations of a qualitative variable. And of course, in the class, we are going to go over more of the interpretations of this qualitative variable. But at this time, I think it's a great time for you guys to start practicing and trying to play around with these data sets. So that's basically all the basic of the linear regression models. And I hope you guys enjoy this video. And I will see you guys next time in the classification models. I'll see you in the next lecture.